Hi everyone, my name is Gwen, and today we're talking about the lexicon of symbols. So, before we dive into the terrifying anomalies of mathematics, we first have to understand the language. Mathematics is entirely written in a highly compressed symbolic language. So, to the uninitiated, it looks like noodles. But for every symbol, and even the specific letters chosen, it carries deep thematic weight. So, what do I mean by this? Let's talk about the Latin alphabet. So, mathematicians don't just pick letters up at random. Specific letters immediately tell you what kind of math you're dealing with. And so, let's just break down the first section of the lexicon, the alphabet of logic. So, X, Y, and Z. What are these? A lot of people come across them, but they actually are known as the unknown and the space, and they're generally used for spatial coordinates, especially in three dimensions, or as the primary variables that you are trying to solve for in algebra. So, when you see these letters, it means you're looking at a system with missing information, and your goal is to uncover the truth hidden within. So shown in here, it's the equation of a sphere, or xy plus y squared plus z squared equals r squared. So this is known as the equation of the sphere, and it tells us that no matter where you go in the universe, if you square the coordinates of a point and they add up to the radius squared, you're standing on the surface of a perfect sphere. So astrophysicists use this exact geometric relationship to mathematically model the boundaries of planets and stars. So we're also coming up to something we know very well as A, B, and C, or the constants. And they represent fixed, unchanging values. And you see them usually as coefficients in polynomials or the length of the sides of a triangle in the Pythagorean theorem. So unlike variables, which can be anything, constants anchor the equation to reality, and they are the fundamental parameters that dictate the shape of the mathematical universe. So, shown here is the standard quadratic equation. The variables provide the curve, but the constants A, B, and C act as the gravitational dials that physically warp, stretch, and position that parabola in space. And engineers use this formula to calculate, for example, a perfect parabolic trajectory of a rocket launching into orbit. So let's take a look at now t with the little curly bit at the bottom. This is actually known as time, and the great forward moving independent variable in calculus and physics. If you see a t, it means the system is moving, and it means things are changing. Time waits for no one, including mathematicians, and equations parameterized by t describe the dynamic evolution of reality itself. So, in Newton's first equation of motion, which you see over here, it captures the thrill of acceleration, stating that your future velocity is actually just your current speed plus the relentless compounding of acceleration over time. So, it's the fundamental law used in ballistics to predict exactly where a projectile will be at any given millisecond. Now, when you're talking about D, we're going through the letters, and this actually represents the infinitesimal. And it's a vanishing small change, a differential slice of reality like d or dy. And it's the absolute foundation of calculus. So, by zooming in infinitely close, mathematicians can break down complex curves into perfectly straight, predictable lines and called the differential or dx. While simple on its own, dx represents one of the greatest leaps in human logic. The ability to mathematically hold something that is infinitely small but completely never zeros, non-zero. So aerospace engineers use this concept to calculate the exact aerodynamic stress on a single microscopic point, for example, on an airplane wing. So now let's take a look at what we know as the core operators. So we move past letters and into the verbs of mathematics. And these symbols tell you what action is being performed on reality. So we'll take a look at first the accumulator, also known as sigma. And so when you see this jagged symbol, you are adding up a discrete sequence of numbers step by step until you reach the end. And it takes a bit of a chaotic scatter of individual data points and forcefully compacts them into a single unified total. And this is Gauss's arithmetic series formula. So instead of painstakingly adding 100 numbers together, this equation creates a brilliant geometric shortcut. So computer scientists use this exact formula today to calculate the processing limits and time complexity of complex sorting algorithms. The next one we have up is actually called the integrator. It's a long loopy S, and also the source of many people's nightmares. The integral is literally a stretched S for sum, and it means accumulation, but for continuous reality rather than discrete steps. So it finds the total area under a smooth, unbroken curve and perfectly measures the accumulation of a fluid, infinitely divisible world. And over here, the equation is called the definite integral, and it bridges the gap between algebra and geometry, calculating the exact volume of sweeping curved shapes that ancient mathematicians thought were initially impossible to measure. Civil engineers used this to calculate the exact volume of water surging through the curves of a massive hydroelectric dam. And a lot of other measurements, and some of it also applicable to cyber optics. So let's take a look now at rate of change, d over dx. So it's also known as the derivative, and this measures the instantaneous velocity or the immediate mathematical slope of a function at one specific frozen point in time. And it's the ultimate tool for capturing the exact speed of reality in a single motionless snapshot. And known over here, this equation, the power rule for differentiation, it's a simple rule that tells us rapidly how a curve is accelerating upward in the chaotic world of, for example, high frequency trading. Financial algorithms use derivatives like these to calculate the exact instantaneous momentum of a crashing stock. So now let's move on to the Greek alphabet because Latin wasn't enough. So mathematicians turned to the Greeks to represent the deeper geometry of the universe. And what do we mean by this? Let's take a look at an easy one, the delta. Yeah. The uppercase triangle actually means a massive macroscopic change. So when reality shifts significantly, you calculate the delta, and it's the stark difference between where you started and where you end. And so it's entirely ignoring the journey in between. And this equation here is called the difference operator and is the foundation of energy transfer. So in thermodynamics, physicists use delta to calculate the massive heat energy lost when a star collapses, focusing purely on the undeniable final impact. Bam. So let's now take a look at epsilon, or the margin of error. So this represents a really arbitrarily small, almost non-existent positive quantity. It is the mathematical definition of close enough, and in the rigorous proofs of calculus, epsilon is used to trap limits, proving that a function converges to an absolute truth. So in epsilon delta limit, it's the ultimate safeguard of logic, and it proves that a variable can get agonizingly close to its limit, and it shrinks the gap until it is smaller than any number you can possibly imagine. So computer software uses this logic to guarantee that a machine learning model converges safely without exploding into infinite errors. So now let's take a look at the spread known as sigma. So in statistics, the representation of the symbol is for standard deviation, and it tells you exactly how far apart, how spread out, and how chaotic your data really is. And a small sigma means predictability and order, while a large sigma means absolute unpredictable chaos. And so in the formula of the population standard deviation, It's breathtaking because it literally quantifies uncertainty. In quantum mechanics, for example, physicists use this exact concept to measure the inherent, inescapable uncertainty of a subatomic particle's position in the universe. So, finally, we are looking at set theory and logic. We reach the grammar of mathematics and the symbols that define the absolute logical boundaries of the universe. So, for the universal quantifier, it means for all, the upside down A. And this flip thing, this means a statement is universally true for every single possible value in existence. And this is no exceptions. It's one of the most powerful and dangerous claims a mathematician can make, but it's because a single counterexample will destroy the entire theorem. And so this is what we call the trivial inequality. And it claims that for every real number in the universe, squaring it will always yield a positive result or zero. And this sweeping invincible truth governs the laws of physics, proving that absolute zero energy is a hard boundary in reality. So now that you've talked about about that, let's think about the existential qualifier or the mirrored E. So it means there exists. It means that in the vast, infinite expanse of mathematics, there is at least one value that makes the statement true, and you don't necessarily know what the value is or how to find it, but you have rigorously proven that it is out there somewhere. And this is existential proof. It represents the thrill of the hunt, providing that a solution fundamentally exists within the universe. And in modern cybersecurity, cryptographers use existential proofs to guarantee that the decryption key exists, even if it would take a supercomputer a billion years to actually find it. So, next, we're looking at what we call the empty set, which is kind of like the zero with a strike. And the set contains absolutely nothing, the mathematical equivalent of a terrifying infinite void, and it's the absolute zero of set theory, and the foundation from which all other mathematical structures are built. And so, in the axiom of disjoint sets, you've got a description of two completely separate worlds, stating that the overlap between set A and set B contain absolutely nothing. Database architects use this exact mathematical logic to guarantee that two highly classified sectors of computer memory will never catastrophically cross contaminate. So, as the outro, as the end of this one, thanks so much for watching. The next episode in this series is actually Zeno's paradox, where we will actually mathematically prove that motion is entirely impossible. What does that mean? See you there for the next one.